The objective of this experiment was to observe Newton's second law of motion by observing an object moving at constant velocity and analyzing it with the tracker program and comparing it to a predicted computational model of the same motion. In doing so, I recorded the video of a cue ball being struck and moving along the width of the pool table. In the initial impact, the ball gains speed until it moves at a constant rate and eventually falls into the corner pocket and stops. To use the tracker software, I set the coordinate system so that the center of the ball would be at the origin and the movement to the right would correlate to the positive x direction. However, it is very difficult to record a video directly perpendicular to the direction of motion. The x-axis may be slightly shifted from the actual direction of the ball by a few degrees and may have led to some error. Then, in order to get accurate data, I calibrated the video by using the diameter of the ball that was given in inches and had to be converted to meters. In order to observe Newton's second law of motion, and that an object moving at a constant velocity experiences no net forces, I chose an interval of time after the ball was hit and before it entered the pocket, which was between frames 234 and 251. After running the program, I made a list of the important data points for the analysis, including noting that the mass of the ball was 0.16 kilograms, and the diameter after being converted to centimeters and meters was 0.005715 meters. The observation start time was at 0 seconds. The initial position was at 000 meters. The last observation of time was at 0.566 seconds. The final position was 0.59400 meters. From this, assuming constant velocity, we conclude that the initial velocity and the final velocity are the same as the average velocity. To find the average velocity, we use the formula of the final position minus the initial position divided by the change in time. From this, we get that the ball travels an average velocity of 1.0495 meters per second in the positive x direction. From this information, I proceeded to make a model that predicts the motion that should have occurred assuming Newton's second law. First, we input the mass of the ball into the computational model. Then, we change the velocity vector to reflect the average velocity we calculated. Because the section of the video being analyzed was only about half a second, I decided to change the delta V to 5/1000ths of a second for better accuracy. When I got to the loop portion of the code, I used a net force vector of 000 to reflect Newton's second law, by which an object moving at constant motion experiences no net force. Then I fixed the final velocity function and the position function to be able to reflect any motion adhering to Newton's second law. When we run the program, we can see that the graph of the model is very similar to the graph of the position over time in the tracker program. And the second model predicts motion in the positive x direction as occurred in the experiment. Because we know that an object moving at a constant velocity should have a constant slope in a position versus time graph, we can make a plot of both the model and experimental data to see just how accurately they reflect Newton's second law. We can see that the experimental data, shown by the blue points, show very little divergence to the model prediction, meaning that the experiment was very successful, and that the constant slope suggests that there was little to no net force acting on the object for the chosen segment of the video.